So good morning. Today we will start our next topic. Topic name is surface tension. So we will discuss about surface tension. Now what is surface tension? Just to understand this, let us take a ring. Okay, this ring is having a handle. Now you dip this ring and let us put a thread like this, loosely bind. Thread is in between as a diameter. Okay, this thread is put inside this ring. Now if you dip this ring in a soft solution, what will happen? Soft solution or in a shampoo solution, what will happen? Entire ring will be filled up with the soft film. Okay, a layer of shampoo or layer of soft solution will be there. Now if you puncture one of this half, say this half, what will happen? So this is the ring. Now if you puncture this half, what will happen? This part of the film will break and this string gets tightened like this. Film is there on the top, but it is being pulled up. You see, this is a practical demonstration of surface tension. What happens? What is happening? When I am puncturing the lower half of this film, the loosely pounded this string gets pulled up by the upper layer of this film. It means that this soft film is pulling this thread up. So there is a tension on the surface which is pulling the thread in upward direction. This is called surface tension. So the liquid layer has a tension on its surface. This we will study today about surface tension. Now before studying about surface tension, we have to understand some other concepts of physics like intermolecular force. Every molecule of a liquid attracts other molecule. Every molecule of a gas attracts other molecule. A liquid molecule or also attracts a solid molecule. Suppose in a glass you have taken water. So water molecule attracts each other. Glass molecule, water molecule attracts each other. So this force of attraction between two molecules, this is all the time, this force is attractive force. This is called intermolecular force. Intermolecular force. This is a very short range force. What is short range force? A force, short range force. If we keep the molecules away, far away, then this force will not be felt. Okay, this force comes into play only when the distance between them is very small, then only this force is effective. So a molecule attracts other molecule with a force. This force is called intermolecular force, and the intermolecular force is a short range force. This is clear? Okay. Now depending on types of molecules, what type of molecule is attracting other molecule, depending on the type, we have two types of force. One is called cohesive force. Cohesive. What is cohesive? The term cohesive means same. The force of attraction between two water molecule, two liquid molecule is called cohesive force. The force of attraction between two similar molecules, solid, gas molecules, this will be called as cohesive force. So between similar type of molecules, the force of attraction, the intermolecular force of attraction is called cohesive force. and the opposite is adhesive force. Adhesive force. What is adhesive force? Suppose you have a water molecule and a glass molecule, solid molecule. Okay. So when the two molecules are different, then the force of attraction between them is called adhesive force. Adhesive force. Okay. Cohesive means similar type of molecule. Adhesive means two different types of molecules. Okay. So now it is clear that there is a force of attraction between the molecules of a liquid or solid and liquid, or between two gas molecules. Okay. Now we will study about the next part, that is called the next topic is sphere of influence. So we will discuss about sphere of influence. What is this? What is the sphere of influence? Suppose let us take a beaker, a container containing the water or any liquid. Okay. Okay. Now here inside, well below the free surface, this is free surface. What is free surface? The surface in contact with air is called the free surface. So let us take a molecule well below the free surface. I'll use a different pen for this. Let us take a water molecule here. Okay. Now this water molecule can attract other molecules, all the molecules within the range of this. Okay. So it has a range up to this much, it is effective. So this force, this distance is called intermolecular range. So what is intermolecular range? A new term comes here. What is intermolecular range? Up to what distance it can impart an attractive force. That distance is called intermolecular range. So within that range, if you draw a sphere, because it's a three-dimensional thing, so you will get a sphere. Okay. It is 3 dimensions. So inside the beaker, the liquid is at the center of the sphere, and all the molecules within that sphere will be attracted by this central molecule. All these molecules on the periphery, on the circumference, as well as inside the sphere, all will be attracted by this. Okay. Now if we consider this molecule, it is attracted by this molecule attracts other molecules. Okay. Now if you consider what is the net force on this molecule, so all the molecules will attract the central molecule in this direction, as well as all the molecules will attract the central molecule in this direction. So diametrically opposite direction. So the net force on this molecule will be 0, because it is attracted by these molecules. It is also attracted by these molecules. So diametrically opposite direction, two forces are acting. You understand? So all these forces will cancel each other. So net force on this central molecule will be 0. Why? Because as many molecules are there in this direction, those many numbers of molecules are also there in this direction. So if you consider what is the net force on the central molecule, which is present at the center of this sphere, so you will find that the net force acting on this central molecule is 0, because diametrically oppositely situated molecules cancelling their impact mutually. Okay, they are mutually cancelling the force. So in other term, we can say this central molecule is free. It is free from any force. The net force on this central molecule is 0, so it is free to move. So inside the molecule, when we consider a molecule well below the free surface with the radius as intermolecular range, this imaginary sphere, this is an imaginary thing just for to conceptualize, to understand in a better way. We have imagined this sphere. So this imaginary sphere is called sphere of influence. So what is the physical significance? Why we are studying this sphere of influence? When the sphere of influence is complete, the molecule is free. So when the sphere of influence is complete, when the liquid molecule is situated far below the free surface. Now if we consider a molecule on the surface or near the surface, if we can consider a molecule here also. So right now we have shown you that you can consider a molecule well below the free surface and the net force on this is 0. Okay. Now let us consider a molecule here on the surface. So what will happen? Its sphere of influence is not complete. With the intermolecular range as radius, you have drawn this. So this molecule is attracted towards this, this is cancelling each other. There is a molecule which will attract it, but there is no other molecule, it is air only, there is no water molecule. So similarly this is attracted by this, but there is no molecule above it who can cancel it. Okay. So if you look at this central molecule and if we divide all the forces, suppose this is attracting, these molecules are attracting this central molecule in this direction. Okay, so we can divide this force into two mutually perpendicular components. Diametrically opposite. So this molecule, this particular molecule is attracted by this. So this force can be resolved into two components. One is along the direction of surface and along perpendicular to the direction of surface. Similarly, this force can be divided into two parts, along this direction, along this direction. Similarly, there are molecules here in this line of action. So here all the forces, these forces can be resolved into two components. One is vertically downward direction, other is horizontal direction. You know now, a force can be divided into two mutually perpendicular components. Suppose this is a force, this is theta. So what happens? We can resolve this force into two components. Horizontal component is F cos theta and vertical component is F sin theta. So here also all the forces are divided into two components. One is along horizontal direction, other is along vertical direction. Now these forces will cancel each other. Horizontal forces will cancel each other because as many molecules are there in this side, those many molecules are present in this side also. So horizontal components are mutually cancelling each other. But there is a net vertical downward direction, there is a net force in the vertical direction. So that is the reason this molecule cannot leave the surface. Okay, there is a inward vertical directional force which is binding the molecule on the surface. That is why the liquid molecule can travel freely inside this liquid but cannot escape the surface of the liquid. The reason is very simple, because it is in a cohesive force field. It is in the force field of all the molecules which is tightly binding the molecules in the downward direction. Okay, so liquid molecules are not free on the surface of the liquid wherever their sphere of influence is not complete. So what we have with this concept of the sphere of influence, okay, we studied that the molecules well below the free surface are free to move, but on the free surface they are not free to move, they are bounded by inward force. Okay, now this is the reason these molecules possess energy. So energy possessed by the molecule, because of its existence in the force field, this energy is called potential energy. Potential energy is what? Energy possessed because of presence in the field. It may be magnetic, it may be gravitational, it may be electric. Okay, But if because of their position in the force field, whatever is the energy possessed is called potential energy. So we call it surface potential energy. Surface potential energy. So the molecules on the free surface are under a inward cohesive force field. That is why the molecules of the liquid possess some energy, and the energy of all the molecules present in the free surface is called surface potential energy. Okay. So sphere of influence you understood, surface potential energy you understood. Now the question that is normally asked, okay, why liquid drops are spherical? Why? What is the reason that the liquid drops are spherical? So if you have given a given volume of liquid, okay, we can convert it into different geometrical shape, okay, and we found that if it is a sphere, then only the surface area is minimum. If it is, had it been any other area like rectangular or three-dimensional, okay, so only sphere has a minimum surface area. Now the answer to this question, why liquid drops are spherical? Because liquid drop, because of its shape, wants to minimize its energy. Minimize energy. Nature favors minimum energy state. Nature always favors minimum energy state. So when the liquid is in the form of a sphere, the surface area is minimum. Surface area is minimum. If the surface area is minimum, the number of molecules will be minimum. So energy will be minimum. Okay. So in order to minimize the energy, surface potential energy, to minimize surface potential energy, liquid drops are spherical in shape. Okay. Now if you want to make the liquid drops escape from the surface, then you have to heat it, you have to give some heat energy, then only liquid drops will get energy and escape. This process is called evaporation. Clear? So we will pause a little and then start again. So why liquid drops are spherical in shape? Because if the drops are spherical in nature, then the surface area will be minimum. And if the surface area is minimum, then the number of molecules on the free surface is minimum. Okay. The energy possessed by all the molecules on the free surface is called surface potential energy. So surface potential energy is proportional to surface area. Higher is the surface area, higher will be the surface potential energy. So liquid drops are spherical to minimize their surface potential energy, because nature favors the minimum energy state. Okay. So for a given volume of liquid, if it had it been other shape, so only spherical shape has the minimum surface area. This can be proved through calculus also, but for the time being you just understand that liquid drops are spherical to minimize their surface potential energy. Okay. Now we come to surface tension. What is surface tension? Surface tension is the hypothetical force acting on the surface per unit length to contract. This force acts to contract the surface area. Okay. So surface, what is surface tension? The hypothetical force, the imaginary force acting parallel to the surface area, okay, in order to contract the surface per unit length. Okay, per unit length. It is not a force. Its unit is not Newton. It is force per unit length. Okay. Suppose the free surface, this is the perimeter. Okay. R is the radius of this surface. So what is the perimeter? 2 pi r. Okay. Now this force acts on the parallel to the surface. This is surface tension force. So what is surface tension? Force acting divided by the length of the total length. So this is force per unit length is called surface tension. So what is the unit of surface tension? Newton per meter. This is the unit. What is dimension? Newton force is mLT to the power minus 2 by L. So M T to the power minus 2. What is unit? Kg per second square. Correct? So surface tension is force per unit length. It is not Newton, no? Remember, it is not a force itself, it is force per unit length. Okay. Surface tension depends on temperature also. Surface tension depends on the nature of liquid. So we will discuss about the factors affecting surface tension in our next video, where we will study about more numericals and exceptional cases of surface tension. But for the time being, just to understand the basic concept, what is surface tension is enough at this stage. Now, what is excess pressure inside a soap bubble? Excess pressure inside a soap bubble. Excess pressure inside a soap bubble. You see, like a shampoo or soap bubble, you can form a bubble. Okay. What is there in a bubble? There is air inside, and this is the film of soap, okay, or shampoo. There is a coating of soap. Now the surface is curved. You see, the surface is curved. It is not a straight surface. Straight surface means what? Pressure on both sides are same. Curved surface means what? Pressure on this side is more than the pressure on this side. Okay. The pressure on both the sides are not equal. So the curvature of the soap bubble indicates that pressure inside and pressure outside are not same.
Pressure inside is.
Okay. So there is a pressure difference. Now the question is, if there is a pressure difference, then there should act a force. It should be unstable. But for some time it exists. Whenever there are different ways to generate bubbles, you have seen. We can generate bubbles and it stay up to some time, and then it dies out. Okay. So what is the reason? Even if there is a difference in pressure, but it is stable. Okay. So there must be something which is balancing this excess pressure. So here we will study about how the excess pressure inside a soap bubble is balanced. Who is balancing the excess pressure? It is the surface tension which is balancing the excess pressure. Okay. So because of the surface tension, this excess pressure is balanced and it remains in the form of bubble for some time. So what is the relation between excess pressure and surface tension? Let it be clear. Okay, we will do some calculation and understand what is the how the surface tension balancing the excess pressure. Okay, let us cut this sub bubble by horizontal plane. Okay, the cut section will appear like this. This is a cut section. Here the surface tension force acts parallel to the surface. You understand, no? This is a three-dimensional figure. I have shown it in two dimensions, so you have to understand. A cut section of the sub bubble is taken, and along, I told you that along parallel to the direction of surface, the surface tension force acts. So in this, if R is the radius, suppose R is the radius, suppose P is the excess pressure, difference in pressure, okay. R is the radius of the sub bubble, and S is the surface tension. So we are finding what is the relation between this. So how much is the force acting? If R is the radius, then the perimeter, the total length will be 2 pi r. So I told you that surface tension is force per unit length. So what will be the force? Force because of surface tension is what? Surface tension into length. So force because of surface tension equal to the surface tension into the length. Length means length of the periphery, length of the circumference. Length of the circumference, if it is r, then the circumference is 2 pi r. So this is what force due to the surface tension. Okay. And what is excess pressure? P is the excess pressure. And what is the relation between pressure and force? Pressure is force per area. So what is force? Force is pressure into area. So this is force due to surface tension, and this is force because of excess pressure. Excess pressure. How much? Force due to excess pressure will be equal to what? Pressure into area. Pressure into area. What is the area? Pi r square. Okay. Pi r square. Okay. Now, surface tension force acts. There are two free surface area. In a soap bubble, there are two free surface area. Because air is inside, air is outside. Okay. But in a water drop, there is only one surface area. Water drop has only outer surface area. There is no pressure inside. So for soap bubble, since in inside and outside there are two free surface, so you have to multiply it by 2. This is only in case of soap bubble. We are multiplying it by 2. Okay. Now in a steady state, excess pressure due to force due to excess pressure should be balanced by the force due to surface tension. Correct. So we will equate this to force due to surface tension is S into 4 pi r, and force due to excess pressure equal to P into pi r square. Correct. So pi cancel out, one of the r will go. Okay. So pressure is equal to how much? 4s by r, or S is equal to this is 4s by r. Okay, or surface tension is equal to P into r by 4. So anyway, you can represent it like this. So what is the relation between surface tension and excess pressure? Excess pressure is equal to 4 times the surface tension divided by radius. But in case of droplet, P equal to 2s by r, because there is only one free surface. Yeah. So now things are clear that because of excess pressure there is a force acting, and this force is balanced by the surface tension force. So we have calculated the surface tension, force due to surface tension, we have calculated force due to excess pressure. At equilibrium state, these two forces must balance each other. So there is a definite relation between pressure and surface tension inside a soap bubble. So this is a very important topic. How does a soap bubble exist when there is a difference in pressure? Okay, because the answer is because this force due to excess pressure is balanced because of its surface tension. Clear? Okay. Now we will move into our next topic. Now let us see what is capillarity. Capillary tube, you heard about capillary tube, small tubes having very small diameter are capillary tubes. Okay. Suppose I have taken a water in a container, in a beaker, and capillary tubes of different diameters are inserted like this. There is a holder. So what will happen to it? The liquid inside the capillary tube rises by itself. Have you seen it? The liquid will rise itself. This rise of liquid inside a tube by itself is called capillarity. Okay. Jurin was the scientist who discovered that if the radius is more, then the height of liquid inside the tube will be less. So height attained is inversely proportional to the radius of the capillary tube. Okay, this is Jurin's law. So if it is very thin tube, the liquid will rise to a higher height. If the diameter is more, then liquid will not raise up to that much height. Okay. So now question is, why this liquid rises by itself? Why there is a upsurge? Why the liquid rises inside the tube? What drives it? Okay. So let us understand this Jurin's law. How we will now set up a relationship what is surface tension and how surface tension helps to raise the liquid inside the tube. Okay. So capillarity, you understood? Capillarity means the rise of liquid inside the capillary tube by itself is capillarity. Okay. Now I will show a very thin tube but in a magnified way. So this is a magnified tube, capillary tube. Actually the tube is a hair like diameter, okay, very thin tube, but I have shown for the sake of understanding. And there is a liquid taken. So suppose the liquid may be water. You have taken water here. Whole thing is shown in a magnified way. Okay. So the liquid will rise in this tube, and shape of the liquid will come to this. What is the shape of the water meniscus? This is called meniscus. This is the free surface area of the liquid. Okay. Okay. So see, at every point of contact, okay, there is a force acting. This is called the surface tension force. Okay. This is a surface tension force. Achha. Now there will be reactionary force. Okay. If this is theta, then we can resolve this force, reaction force, into two components. One is r cos theta, other is r sin theta. Correct? Resolution of a vector into two components that we have seen in vector. So every point, wherever, because it's a three-dimensional figure, every point in this three-dimensional tube, everywhere there is a vertical component. What is R? R reaction is nothing but the surface tension. So S cos theta is acting along vertically upward direction, and S sin theta is this. So all the if you take all the molecules, this horizontal component, because of its position in diametrically opposite direction, this R sin theta will cancel each other because they are diametrically oppositely situated. So these two components will cancel out. So what is the net force along upward direction? It is R cos theta. So R cos theta is acting only on these two molecules? No. R cos theta is applicable to the entire surface area. Okay, to the entire surface. So what is the total force because of surface tension acting along upward direction? It is R cos theta into the length of this boundary. So if R is the radius of this capillary tube, then the length of the boundary will be how much? 2 pi r. So it is 2 pi r. So R is nothing but it is balancing this surface tension. So S cos theta into 2 pi r. So it is 2 pi r S cos theta. So this is the force because of the surface tension. Now, will it move and up and come out in the form of fountain? No, it is not happening like that. Okay, what is happening? It moves up to certain extent, and then it stops rising. Why? Because now the gravitational force comes into play, because the mass of the liquid inside the tube is more. So gravity is pulling it downward. Okay, so as long as surface tension force, because of the force due to surface tension is more, the liquid raises up. But the moment the liquid raises up, its weight increases inside the tube, the gravitational force pulls it downward. So the moment gravitational pull is equal to the force due to surface tension, there is a equilibrium state. So liquid stops rising. Correct? So what is the force due to gravitation? Force due to gravitation is mass into g. What is mass? Suppose this is the height h. What is the mass inside this cylindrical tube? Volume into density. So volume is what? Pi r square h, cylindrical volume. Density of water, suppose consider it as rho. Correct? Into g. So this was the force due to surface tension 2 pi r s cos theta, and this is the force due to gravitation. Okay. So at equilibrium, when the liquid stops rising, these two forces are equal. So let us balance it. 2 pi r s cos theta equal to pi r square h rho g. So one of the r cancel out, pi cancel out. So s is equal to r h rho g by 2 cos theta. So what we have derived as surface tension equal to h r h rho g, r h rho g by 2 cos theta. So this is the relation between the surface tension and this. Okay. Now say here h and r are reciprocally related. If you keep here h, then what will be this? H is equal to s by r rho g. This is Newton's law. H is inversely proportional to the radius. Yeah. H, surface tension is constant for the liquid. Theta is angle of contact, that I will explain you. Theta is angle of contact, but these are constant for this liquid and glass. R is the radius of the capillary, which you can vary accordingly. Rho is density of the water, that also varies if temperature remains same, and g is the acceleration due to gravity at that place. So what is happening? The height is inversely proportional to the radius of the capillary tube. This is Joule's law. So if you want to measure the surface tension of glycerin or water or kerosene oil, anything, put a capillary tube, measure the radius of the capillary tube, measure the height up to which it is raised, you know the density of that liquid, you know the acceleration due to gravity at that point, and you have to know the angle of contact, then you can find out the surface tension of the liquid. So we'll have in your standard 11 and 12, we have an experiment to measure the surface tension practically. So we'll study that part also. But right now you understand that this is the relation. This is the reason why liquid rises. Okay. Now in this calculation there is a mistake. What is the mistake? Mistake is, if you just think this part, okay, let me use a different color pen for this. We are assuming that the entire liquid is in the form of a cylindrical layer, okay, but actually this is a meniscus. See, there is an empty space here, correct? So we are measuring height up to this level. What happens to this liquid which is inside the water meniscus? We have to take account of that liquid part also. So minor correction is required in this formula. This is okay for simplification, for simplified result. This formula holds good. But if you go into the detailing of it, then you have to take into account this part of it also. Okay. So let us take this water meniscus, that is the liquid inside the water meniscus, to be considered. Okay. Okay. So suppose, for the simplification sake, how to find out the liquid inside meniscus? This is a small cylinder minus this is a hemisphere, correct? So if we subtract the volume of a hemisphere from a cylinder, then we can get the volume of liquid inside the water meniscus, excess water. Okay. So what is the volume of the cylinder? Pi r square into h. H is nothing but the radius r, pi r cube. Okay. Minus, what is the volume of the hemisphere? The volume of the sphere is 4 by 3 pi r cube. Okay. Now for the sake of simplicity, we have taken that this and this are same. Okay. This radius and this height are same. Okay. So what is the hemisphere volume? It is 4 by 3 by 2. So it is 2 by 3, correct? So it is 2 by 3 pi r cube. So this gives the volume of the liquid inside the meniscus. So it is 3 pi r cube minus 2 pi r cube. So it is pi r cube by 3, correct? So what is the total mass of the liquid of height h? So now we are calculating the force due to gravitation. Total mass means up to this much, pi r square h into g, plus mass of the liquid inside the meniscus is this much. This is the volume, pi r cube. Volume into density is mass, into g is the force. Okay. So now we have this relationship. So we can take pi r square and of course there will be density. This is volume into density into g. Okay. Pi r square rho and g can be taken common. So what is happening here? 1 plus, there is a r left, r by 3, and there is a h here. Okay. H plus R by 3. And force due to surface tension is same, that is total length of the boundary into R cos theta into S cos theta. Okay, so the force due to surface tension is what? Total length of the boundary is 2 pi R into surface tension. The force due to surface tension is R cos theta, R is S, so it is S cos theta. Now at equilibrium, this gravitational force is balanced by this force due to surface tension. Okay, so now I will remove this picture to give you the detail of this calculation. Okay, so at equilibrium, force due to gravity is pi R square rho G H plus R by 3. This is balanced by force due to surface tension 2 pi R S cos theta, 2 pi R S cos theta. Correct? So pi cancel out, one of the R goes. Okay, so surface tension equal to R rho G H plus R by 3, correct, by 2 cos theta. Now if the radius is very small, capillary tube means hair-like diameter, okay, very small diameter, then if R by 3 is very small compared to the height attained by this liquid inside the tube, then we can ignore this R by 3 and it becomes S will nearly equal to R rho G H by 2 cos theta, which is same as this. Correct? So this is the relation between the height attained by a liquid inside a capillary tube and surface tension in terms of angle of contact, density of this tube and radius of this tube. Okay. So next topic is angle of contact. Angle of contact. See, if you take a liquid inside a tube, so the angle made, see here, this is the point of contact. These are the point of contact. In 2 dimension, I can only show you 2 point of contact, but actually in 3 dimension, in a tube, inside the liquid, there are many points of contact in the circumference. Okay, so at every point of contact, you draw a tangent to the free surface, and you draw a tangent on the container, on the wall of the container. Okay, so whatever is the angle between these 2 tangents is called angle of contact. So right now, for simplicity's sake, I have taken a vertical, means rectangular beaker sort of thing, but I can take a curved container like this. Here I have taken a liquid. Okay, so how to find out angle of contact? At this point of contact, okay, at this point of contact, you draw a tangent to the free surface. This is a tangent, okay, and draw a tangent to the container wall of the container. Correct? So this is the angle of contact. So what is angle of contact? Angle of contact is the angle between the free surface and wall of contact between the 2 tangents drawn at the point of contact. Okay. Now, some of the free surfaces are not concave. Okay. some of the free surface like mercury. See, if you take a mercury inside a glass tube, what you'll see mercury is like this. The shape of the free surface is convex. Okay, it is convex. In water inside a capillary tube, it is concave. I will explain why this free surface is convex, why this free surface is concave. Okay, but here, how to find out the angle of contact? So, wherever the free surface touches the wall of the container, at that point you draw a tangent here, tangent on the free surface. Okay, so this is the free surface, so tangent will be like this, and on this wall, this is the tangent, so this is the angle of contact. Now, if you take a, suppose I have taken a container like this, and I have taken mercury inside it, correct? How to find out the angle of contact? So, at the point of contact, you have to draw two tangents. One is this, other is this. So, this is angle of contact. So, now it is clear. Now, why free surface of mercury is convex and free surface of water is concave? So, now the answer lies in the fact you have understood intermolecular force. There I told you about two type of forces. One is cohesive and the other is adhesive. In case of mercury, this cohesive force for mercury, this cohesive, mercury is denoted by Hg, okay? Cohesive force is greater than the adhesive force. This is much greater. Cohesive force, that is the force between mercury-mercury molecule is much more than the force between mercury and glass molecule. So, if cohesive force is greater than adhesive force, the angle of contact is obtuse, theta is obtuse. Obtuse means more than 90 degree. Okay, but for water, adhesive force is greater than cohesive force. Hence the angle of contact is acute, less than 90 degree, acute, less than 90 degree. The free surface is concave in nature. So this explains all the thing, angle of contact, free surface, all together. So let me revise what we have done in this class today, and you come and explain what you have understood, okay, one by one, so that we are on the same page. We explained intermolecular force, cohesive and adhesive, correct? Then second term came sphere of influence, then surface tension, surface potential energy. Here also surface potential energy, this is very important actually. While liquid drops are spherical in nature, surface potential energy, then surface tension. Then we studied about relationship between surface tension, Joule's law, surface tension, height raised inside the liquid is proportional to the radius of the capillary tube. Okay, so relationship between the surface tension and height attained inside the liquid tube. Okay, then we explained what is angle of contact. Angle of contact. While explaining angle of contact, We explained shape of free surface. So can you come and explain? You understood?
Okay, so the first point is intermolecular force. Intermolecule, when there are in an element, when two molecules attract each other, the force by which they attract each other is known as intermolecular force. We understood that there are two types of intermolecular force. One is cohesive and one is adhesive. Cohesive force means the force between two molecules of the same type of molecules, like two water molecules, when they attract each other, the force between them is cohesive force. And adhesive force is when there are two different type of molecules, like one molecule of water and another molecule of glass. When they both attract each other, the force between them is known as adhesive force. Then we understood about the sphere of influence, which says that the force acting on the body which is inside the liquid is zero, because the force acts diametrically opposite. Okay, so the force that it's actually the sphere of influence. The sphere is an imaginary thing which helps us to understand that the molecules which are inside the liquid, which are like below the free surface, they have zero force acting on them, because the force acts diametrically, because the force acts in diametrically opposite directions, and neutralizes each other. Next, we understood the surface potential energy. In this, we took an example of that why the why the water droplets are small. This is because
Spherical, not small, spherical.
Sorry. Why the water droplets are spherical? Because our nature favors minimum energy. So if the water molecule is spherical, then it will have minimum surface potential energy, because sphere is the only shape which has minimum surface potential energy. If it was a
minimum surface area.
minimum surface area. If it had been a cube or a cuboid, it would cover a much larger surface area. For that, the surface potential energy will increase. The surface potential energy is the energy that is being held by the molecules which are on the free surface. Okay, next we understood surface tension. We also understood the relation between surface tension and excess pressure, which is just a second.
In a soap bubble, there are two.
P is equal to 4S by R.
And water droplet.
In a water droplet, it will be 2S by R, because in a soap bubble, the inside is not filled by anything. Like in a soap bubble, inside it's only air. So there are two free surfaces, one inside and one from the outside. But in water molecule, inside it is not empty, it's filled with water. So there is only one free surface, that is from the outside. So the relationship between excess pressure and surface tension in a soap bubble would be P is equal to 4S by R, because it has two free surfaces, and in water it will be P is equal to 2S by R. Then angle of contact. We also understood about the angle of contact, how to determine the angle of contact. Suppose there is water here. So the angle of contact, we will draw first a tangent through this area and one vertical line through the surface. So this will be the angle of contact. We also determined angle of contact if it would have been a convex meniscus. So it will the tangent will be drawn here and another will be here. So the angle of contact will be this.